Hello students, welcome to video tutorial class. Today's video is meant for BA BSc first semester 4 years undergraduate program under NEP. In this video, we will discuss the consistency of linear system of equations in matrix algebra. So let's learn how to find the consistency in linear systems. Let's proceed. This topic is taken from Unit 3 of your syllabus, Classical Algebra. To learn consistency of linear systems, we are considering a non-homogeneous linear equation. Homogeneous linear equation, the constants b1, b2, bm are 0 for homogeneous, but now we are considering a non-homogeneous equation, so b1, b2 up to bm will have some values. Okay. Above system can be expressed as a equal this, the coefficient of the variables, x is the variables are here x1, x2, xn. It can be also x, y, z, w, anything, but here we are considering x1, x2, x3, x4 up to xn. And b is the constants b1, b2 up to bm. Okay, non-zero constants. Here A is called coefficient matrix because we are considering the coefficients of the variable, and X is called a variable matrix, that is x1, x2 up to xn, and B is called resultant matrix. Okay, so we are going to study cases, two cases. Case 1, m equals to n and determinant of a not equal 0. Then we can solve the system of equation by using Cramer's rule or by this x equal to a inverse of b, that we are not going to discuss in this video. Here we are going to discuss case 2, that is m equal n or m not equal n. M number of rows, n is the number of columns. For case 2, we are going to consider a matrix C, which is the combination of matrix A and matrix B, that is the coefficient matrix and the resultant matrix. Okay, and this matrix is called augmented matrix. The augmented matrix is of order m cross n plus 1, n columns from the coefficient matrix and 1 column is added from the resultant matrix, so order is m cross n plus 1. Now to find the rank of the matrix C, that is the augmented matrix, we reduce it into its echelon form. Okay, what was echelon form? The leading element should be 1 and the 0 row should be placed at the end, isn't it? Further, what is the rank of C here? Rank of C is the rank of this whole augmented matrix, that is the combination of coefficient matrix A and the resultant matrix B. So let us see this case. If rank of A equal rank of C, then the system of equations are consistent. That is, they have a solution. Okay. Now, in the next case, if rank of C is not equal to rank of A, that is the rank of the coefficient matrix is not equal to the rank of the augmented matrix, then the system will be inconsistent. That is, they have no solution. So, from the augmented matrix, we will get two cases. If rank of A is equal to rank of C, then consistent and they have a solution. Rank of A is not equal to rank of C, then the system is inconsistent and they have no solution. Again, let us consider that rank of C is equal to rank of A is equal to R, is equal to some R. R is the rank. Okay, that is the rank of the augmented matrix, and the rank of the coefficient matrix A is equal to some non-negative positive integer. So R can be 1, 2, 3, etc. depending on the order of the linear system of equations. So here we are considering the rank as R and we are trying to study two cases, case 1 and case 2. In case 1, if R equals to n, that is the rank is equal to the number of variables. Okay, if variables are x, y, z and rank is 3, then the system has unique solution. That is the number of variables and the rank is equal. Again, in the next case, that is case 2, if rank is less than n, that is the number of variables is less than the rank, then the system has infinite number of solutions. Let's proceed to an example and try to understand the consistent and inconsistent of linear system of equations. Examine if the following system of equation is consistent or inconsistent. If consistent, find the solution of the system. So we are given a system of equations. Here, what is n? N is equal 3. How 3? The variables. N means the variables x, y, z. So x, y, z, n is equal 3. And now if this linear system of equations is of rank 3, it is of order 4 by 3, and if its rank is 3, then the system will have unique solution, that is it will have only one solution. And if r is less than n, that is rank is less than the number of variables, then the system will have infinite number of solutions. Let's proceed to solve the given system of equations. So the given system of equations is this, and we will write the equations in matrix form. Okay, matrix form, that is the coefficient matrix, the variable matrix, and it will be equal to the resultant matrix B. So 1, 2, minus 1, 3, minus 1, 2, 2, minus 2, 3, 1, minus 1, 1. And the variables are x, y, z. And it will be equal to the resultant matrix, that is 3, 1, 2, minus 1. Hence, the given system of equation is written in matrix form, that is Ax equal B. Now we will form a augmented matrix by combining the coefficient matrix and the resultant matrix, and we will name the augmented matrix as C. C equals to A such that B. We read the augmented matrix as A such that B. So the augmented matrix C becomes 1, 2, minus 1, 3, minus 1, 2, again in the next row 2, minus 2, 3, 1, minus 1, 1. So this is the matrix A, 4 by 3 matrix, and then we combine the matrix B, that is 3, 1, 2, minus 1. Here we put a vertical bar to differentiate the matrix A from matrix B. Now we will try to reduce this augmented matrix to its echelon form. So we are going to do row operations, and we are trying to make the first column 0. So row 2, what we will do? We will subtract from row 1 by multiplying the row 1 with 3. That is row 2 minus 3 row 1. Row 3, similarly row 3 minus 2 row 1. And then row 4 minus row 1. We will do all the operations together to reduce the number of steps. So row 2 will be 0, minus 7, 5, minus 8. Row 3, 0, minus 6, 5, minus 4. Row 4, 0, minus 3, 2, minus 4. Now, in the next step, we will try to make the leading elements 1 to convert it to echelon form. So, we will do operations again in row 2. What we will do? We will do scalar multiplication of row 2 by minus 1 by 7. So, we will multiply throughout by minus 1 by 7 in row 2. Row 1 will be same. Row 1 will not change. It will be as it is, 1, 2, minus 1, 3. And then row 2 will be 0, 1, minus 5 by 7, and then 8 by 7. We will do operations in the B matrix also. Okay. So the leading element of row 2 became 1, and the remaining rows will remain as it is. Further, we proceed to reduce the augmented matrix to its echelon form. So for that, we will do operations on row 3 and try to make the leading element of row 3 equal to 1. So for that, what we will do, we will multiply 6 to row 2 and then we will add it to row 3. That is, row 3 we will make row 3 plus 6 row 2. Together we will do operations for row 4 to reduce few steps. So for row 4 what we will do, we will multiply row 2 with 3 and then we will add to row 4, that is row 4 plus 3 row 2. These operations on row 3 and row 4 reduces their leading element to 1 and the remaining rows remain as it is, that is row 1 and row 2 will remain as it is, 1, 2, minus 1, 3, row 1. Row 2 remains same, 0, 1, minus 5 by 7, 8 by 7. The elements of row 3 will change to 0, first element, second element, 0, next becomes 5 by 7 and further 20 by 7. Similarly, after doing the operations on row 4 becomes 0, 0, minus 1 by 7 and minus 4 by 7. This completes the matrix in this step. Further, we proceed to make a 0 row if it's possible. So, again, we will do operations on row 3 to convert the augmented matrix to echelon form. So, in row 3, we will do scalar multiplication of 7 by 5 and in row 4, we will do scalar multiplication with minus 7, and with these two operations in row 3 and row 4 the matrix reduces to the form 1, 2, minus 1, 3, that is row 1 and row 2 remains same because no operation is done in row 1 and row 2. It is minus 5 by 7, 8 by 7. Now row 3 after scalar multiplication with 7 by 5 reduces to 0, 0, 1 and then 4. Okay. Similarly, row 4 after multiplication with minus 7 reduces to 0, 0, 1, 4. Now in the next step we will subtract row 4 and row 3 so that the last row becomes 0, that is the end row becomes 0 row. So the matrix now reduces to 1, 2, minus 1, 3, 0, 1, minus 5 by 7, 8 by 7, 0, 0, 1, 4 and the last row, that is row 4, reduces to 0, 0, 0, 0, that is 0 row. Hence, we can stop the operations here because the required echelon form of the augmented matrix is obtained. Okay, all the leading elements of the augmented matrix is 1 and the end row is a 0 row. So this is the echelon form of C, that is augmented matrix. Now the corresponding form of A is 1, 2, minus 1, 0, 1, minus 5 by 7, 0, 0, 1. We will consider only the matrix A excluding the end row. Okay. So the corresponding form is this and its rank is 3. Its rank is 3. And also the resultant matrix, the B matrix. The B matrix was 4 by 1 matrix. 1 column, 4 rows. And it reduced to 3 by 1 matrix. That is 3 rows, 1 column. So rank of A and the augmented matrix rank of C is equal to 3. Okay. The rank is 3 here. We are not required to find the rank of A individually here because the augmented matrix C itself contains the matrix A and matrix B. So from there itself we can conclude that the matrix A is of rank 3. Okay. You can see here this transformed echelon form is the transform form of the augmented matrix. Okay, the augmented matrix is transformed to this form, and here you see we have only 3 non-zero row, and the end row, that is the row 4, is the null row. Okay, so the equation is consistent. We have 3 variables x, y and z, and the rank of the augmented matrix is also 3, and the rank of the coefficient matrix, that is A, is also 3. So if rank is equal to the number of variables, then the equation is consistent and we have a unique solution, that is only one solution. Since the system is consistent and we have a unique solution, we are asked to find the solutions of the system. Okay, so to find the solution, we write the equivalent matrix equation as 1 2 minus 1 0 1 minus 5 by 7 0 0 1, and then the end row. You can avoid this end row since it is a null row, that is row 4 is a null row, so you can avoid this, you can eliminate this row, but it's okay. The variables were x, y, z, and the resultant matrix was 3 8 by 7 4 0. Okay, this is the resultant matrix. Now we will solve this equivalent matrix and then we will find the solutions of x, y and z. So we will do matrix multiplication. 1 into x, x, 2y minus 1z minus z. Similarly, next row y minus 5 by 7z, and the third row was z, and the end row was 0, which you can eliminate it. And the resultant matrix 3 8 by 7 4 0. Okay, so now we will compare both the matrices in the left hand and right hand side and then solve the equations. So here x plus 2y minus z will be equal to 3 by comparison, and then y minus 5 by 7 z will be equal to 8 by 7, and z will be equal to 4. So z is equal to 4, so we will put the value of z in equation 2 and we will find the value of y. This is a simple algebraic solution, so you can solve it. It's very simple. Put the value of z in y minus 5 by 7 z and then find the value of y. Then put the value of z and y in the first equation and then find the value of x. So we will get a solution set, unique solution set. 8 by 7 plus 5 by 7 into 4. So y will be equal to 28 by 7, that is 4. We will get 3 minus 2 into 4. The value of y is 4 and z is also 4. It will give us, after simplification, minus 1. Therefore, x is equal to minus 1, y equal 4 and z equal 4. Hence, we obtained a unique set of solutions for the given set of equations. In this way, you can solve different system of linear equations and you can find if the system is consistent or inconsistent by reducing the augmented matrix to its echelon form and then comparing the rank with the number of variables. If the rank is equal to the number of variables, then consistent, otherwise it is inconsistent if it is less than n. Hope you have understood how to find a consistent and inconsistent solution in a system of linear equations by the augmented matrix. Thank you for watching.